Hey y'all, welcome back. So today we are going to start off a new unit all about logarithmic functions. But before we really get into what a logarithm is, today we're just going to focus on an idea that you were exposed to in Algebra 2 called an inverse function. So an inverse function is a function that essentially just undoes another function. And what I mean by that is for any function that you might have, like let's say we have a very simple function like f of x equals 2x, right? So basically whatever the input is, the output will be doubled. And you might be able to construct a table of values for this particular function. We have our inputs and our outputs. And for example, if you input 0 into this function, so let's say we just want to like plug in 0 into x, well, our output, if I double that, would just be 0. If I substitute a 1 into x, if I use 1 as my input, then my output would be 2, because 2 times 1 is 2. If I input 3, let's actually go to 2. If I input 2, my output will be 4. If I input, there we go. If I input 3, my output will be 6, and so on and so on. So what you're seeing here is that whatever the input is, the output gets doubled, right? So this is just a real simple function here. An inverse function will undo this, and in effect, what happens is that the domain and the range get swapped from the original function. So instead of this function going from like 0 to 0, 1 gets mapped to 2, 2 gets mapped to 4, 3 gets mapped to 6, and so on. The inverse of this will swap the mapping. In other words, the inputs would be 0, 2, 4, 6, and the outputs would be 0, 1, 2, and 3. So if we were to define the inverse of f here, the way we would write that is with a little -1. It looks like an exponent. You can find my little exponent thing here. Okay, let's just do this. There we go. See f with a little -1 exponent, and the way you read this is the inverse of f of x. Okay, so now what the actual rule here is, we're going to learn how to find that today, but you might be able to figure out just by looking at the table, right? Like if I swap this, if I construct a new table here for x and the inverse of f, this is going to be still relating to that 2x function, but instead of it just being f of x equals 2x, we're looking at the inverse of this particular function. And so while we might not know exactly all the data points here, we can just pick the ones that we see here and say that, well, if I input 0, I'm going to output 0. If I input 2, I'm going to output 1. If I input 4, I'm going to output 2. If I input 6, I'm going to output 3. So you can see that this mapping is just flipped. Okay, it's just reversed from the original function. So what I'm going to show you here is that you don't have to like guess and check your way through trying to figure out what expression can be used to model the inverse function. There is an algebraic way that we can approach this. Okay, so I really want to go back to get you to understand why this works, and kind of just briefly mention like what the inverse is again. So the inverse is just the relationship that maps x to y for some function, but flipped. So the domain and the range are just simply reversed. Like if you have a table of values for f of x, if you want to construct a table of values for the inverse of f of x, you just flip the x and y. And algebraically, that's essentially what you do too. Okay? So if I want to find the inverse of a function, like let's say I've got 2x plus 3 here. And I want to know, okay, well, I don't want to go through the process of like making a table, flipping it, and then trying to decode what the equation would be. I don't want to go through all that. Instead, I'm going to try to find it directly using algebra. So here are the steps. I've got them listed here for you up here, just so you can refer back to them. But the first thing we're going to do is we're just going to replace f of x with y. Okay, so we're just rewriting this equation, but just kind of taking the f of x out of it. I think it'll make the whole thing go a little smoother here. Let's shrink this font size up just a tad. Okay, so the second step And this is really where we start generating the inverse function here, is we're going to swap x and y. Okay, remember that the inverse has the domain and range flipped. So it would stand to reason that if we're finding the inverse, we're just going to swap x and y. Okay, so we basically just flipped the inputs and the outputs. Okay? So once you flip those inputs and outputs, now we're going to rearrange the equation and solve it for y. So we'll have to use those properties of equality that we use to solve linear equations for the most part. There's a few other things here and there depending on what kind of function you're dealing with, but for the most part, you're just going to be using your regular old properties of equality to isolate y. So to do that, in this particular example, I'm going to subtract 3 from both sides. And then I'm going to divide everything by 2. All right, divide this side by 2, divide this side by 2. And then there we go. We've got the y isolated. Now, once the y is isolated, we're going to go back and replace that y because that's not really the same y that we had originally. This is the inverse. Okay, so we're going to name this the inverse of f. Okay, so we're basically going to refer back to the original function here, but we're going to not call it anything besides just the inverse of f of x. Now, this is if you write it like this as a big fraction, that's fine. But I think you're probably better off, like if you were to graph it or anything or want to analyze this, it's probably better that you rewrite this in slope-intercept form. So 1 divided by 2 is just going to be 1/2, so like 1x over 2, or just 1/2 x. And then minus 3/2. Okay, so that would be the inverse of 2x plus 3. For number 2, we'll do basically the same thing here in terms of the steps. So the first thing we're going to do is rewrite g of x as y. And then so we have 2 times the square root of x minus 3. Next, we want to swap x and y. We got x equals 2 times the square root of y minus 3. And now we have to go through the process of solving for y. So first, I'm going to divide both sides by 2. I'm just going to write that as 1/2 x instead of x divided by 2 equals square root of y minus 3. Now I need to square both sides to get rid of that square root. So to square both sides here, I'm going to have 1/2 squared, which is 1/2 times 1/2. It's going to be 1/4. Then x times x is x squared. Finally, I'm going to add 3 to both sides. So I get y equals, well, I'll just leave it like I had the other one. 1/4 x squared plus 3 equals y. Added 3 to both sides, and now I've got my inverse function. Let's see here. Well, let's just go ahead and write it as g for the inverse of g. Right, so this function is named g, so inverse would be the inverse of g. And I'm just going to move all this stuff up, see if I can't squeeze all these all these above that line. It's going to be a tight fit here, but I'm going to do it. There we go. So g of x, or I'm sorry, the inverse of g of x is going to be 1/4 x squared plus 3. Okay, 3 is f of x equals 2x cubed plus 1. So to find the inverse, you're going to start by rewriting f of x as y. Then we're going to swap x and y. So x equals 2 times y cubed plus 1. And then we need to solve for y here. So to do that, I'm going to first subtract 1 from both sides. Then I'm going to divide both sides by 2. And it's going to look kind of like what we have over here, where we divide by 2. But I'm just going to divide each term by 2, and that way I don't have like a big fraction. I'm going to divide everything by 2 here, and that's going to give me 1/2 x minus 1/2 equals y cubed. Like we're just about done here. The last thing to do, or I guess we have 2 steps left. The first of the 2 steps is going to be to take the cube root of both sides, so get rid of that cube. So it's going to look like this. The cube root. You could also write it as this whole expression raised to the 1/3 power. Taking the cube root of something is equivalent to raising it to the 1/3 power. So if you just like your exponents over a radical symbol, you're welcome to do that. But here we go. So we've now found inverse of f here. The inverse of f of x is going to equal this whole expression, the cube root of 1/2 x minus 1/2. I didn't copy that properly. Okay, well, it doesn't. You want to copy that for some reason. That's not copying. There we go. Right, so that is how you find inverse functions. You don't have to like guess and check your way through a table or anything like that. The strategy is to really just swap the positions of x and y, because that's what an inverse is, right? You're just changing the domain and range. So you swap x and y, solve for y, and then rewrite it using this function notation. Now, something that's kind of interesting about these inverse functions is that when you graph them, because they undo each other, they are going to be reflections across the line y equals x. So if all you have is a graph of f of x, you can pretty easily graph the inverse without even really knowing what the equation is. Like I was saying up at the beginning, the tables for a function and its inverse are just swapped. So the points on the curves for these two will also be swapped, the x and the y coordinates. For instance, on this function up here, if you have a point at 1, 2, the inverse will have a point at 2. So if we're going to sketch these inverses given an f of x, given a function, all we need to do is just pick a couple points on there and just swap the x and y and replot the new points. So I'm just going to pick some points strategically here on number 4. Yeah, it looks like we got a point right here. Okay, I'm going to pick this point, which is negative 1, comma, oh, no. This goes by 2. So -2, comma, -6. And if I flip that and get -6, comma, -2, the new point, or the inverse point, is going to be let's find another point. Doesn't really look like the slope's very nice here. So I guess, we could use any point that's actually on the line y equals x, like this point 4, 4. You swap that, you still get 4, 4. And so we know that that point's on there. So if you ever have a point that's on this y equals x line, you can just use that for the inverse as well. Well, lines are defined by 2 points, so that's really all we need here. I'm going to go ahead and draw my line. Make sure I go through those 2 points, and yeah, there you go. Here's our line. It's just kind of a quick sketch here, but notice that this green line is a reflection across that line y equals x. In other words, if you were to fold the graph along the line y equals x, all the points on the function would match up with a corresponding point on its inverse. Number 5 has this little curve. It looks like this could be like a, it's probably a square root function if I had to guess. So we have this point right here, which it's not super obvious what it is, but if I had to guess, if this is 2 and this is 1, it's probably like a 1/2, comma 3, roughly. So if I flip that and go 3, comma 1/2, the point that would be on the inverse would be right here. And let's draw that as a point. Now you don't have to be like perfectly accurate here. You're just trying to get kind of the gist down. And I've got this point right here. It's kind of close enough to this 2, comma 4 It doesn't look like it's exactly there, but just to kind of get the shape down, I think it's safe to say, okay, well, 4, comma 2, kind of have to estimate this position anyway. I'm going to just put that there. Now we do have a point that's on y equals x, so we're going to utilize that as maybe another point to kind of guide our graph here. But once you have enough points here, kind of get a good idea of what the graph should look like, you can just go ahead and start sketching it. It's going to be a little rough here, but I don't really like that. Hopefully with your pencil you can make it look a little bit nicer than that, but it should be doing something like that. Number 6. Okay, this doesn't have, this looks kind of like a cubic function if I had to guess on this one. So I'm going to pick a few points here. Definitely going to pick this point right here that is on y equals x because that's kind of the easiest one to pick. But for the rest of this, we're just going to have to kind of estimate. Now, we've got a nice y-intercept here at 0, comma 2. So the inverse should have a point at 2, comma 0. Do we have any other nice points here? This one right here is at 4, 10. So 10, 4, point here. Really, I'm just kind of looking for these points to help me guide my graph. This one right here looks like it's at -4, -6. We should have one at -6, -4 on the inverse. All right, so that's probably good enough. This is going to be pretty sketchy for a sketch because I'm using a mouse to try to draw this smooth curve. But let's just have at it. Okay, I'm going to go up here. I'm going to pass through this. Okay, and what I want to do is have a nice little inflection point at this axis, kind of come back close to the curve, and then we're going to go back away from it. And then if you kind of tilt your head 45 degrees, it should look symmetrical. It looks pretty decent. I mean, just it doesn't have to be perfect, but there we go. Here's the graph of the image. Number 7 looks like it's if I had to guess, I would say it's probably an exponential function. Now we've got this y-intercept at 0, comma 2. So the inverse should have a point at 2, comma 0. Going to be right about here. And then what else do we have to work with here? It looks like this point right here looks like 2, comma 5. So it should have one at 5, comma 2, roughly here. The more points you can plot, the more accurate it's going to be. You don't need a ton, but you do need some. Now, I'm looking at this little section right here. It looks like once I cross over the axis, the curve just kind of like, looks like it's sort of like trending towards y equals 1, halfway between 0 and 2. So I'm going to I'm going to try to copy that down here. Oops, maybe with the pen and not with the circle. Cool. And just kind of go down this way. Okay. And then I cross over here. It looks like it doesn't pass through the next grid line, so it's going to do something like that. All right. Now I do want to call your attention to this problem specifically because this is going to, this one right here, put a big star next to this one. This is going to guide our discussion for the rest of the unit. Okay, there's something with this one that I'd like to come back to. I'm not going to really go into detail. I know I'm being vague right now. But just know there's a little bit of significance to what's going on in number 7 that relates to our logarithm unit. All right, number 8 says plot the inverse of the function by reflecting the graphs across the line, then complete the tables. Okay, so basically, to start this off, we're going to do kind of the same thing. We're going to first fill out this table here. When x is -1, looks like y is 12. When x is 0, looks like y, that's right here, y is 5, 6, 7. And when x is 1, y is 4. When x is 2, y is 3. Double check, make sure I'm reading that right. When x is 3, 1, 2, 3, y is back up to 4. x is 4, y is 7. Now, when x is 6, we're off the grid, so you know what? I've got to think that this is a typo, okay, because we can't really tell what that is yet. So let's just change that to 5. Because when x is 5, y is 12. We're back up to 12. We have this nice symmetrical table. Now, for the inverse of f of x, we're going to swap the x and y's. All right, so we're going to take all these values we just wrote down. Instead of using those as our y values, we're going to use those as our x values. And then for our y values here, we're going to use the original x values. So basically, we're just taking this table, we're just swapping all the numbers. So there should be -1, 0, 1, 2, 3, 4, and 5. Now, the function here is x squared minus 4x plus 7. I'm going to be honest with you. This is not, I'm never going to give you one that's going to be this complicated as far as like trying to find the inverse function. However, that being said, let's see if we can't plot this and see what we get. Now, got 12 comma -1. Is that even going to fit on here? Let's see, 5, 6, 7, 8, 9, 10. No, so let's just skip that one. 7 comma 0. 4 comma 1. 3 comma 2. 4 comma 3. So we're backing over here. And 5 comma, oh wait, no, I skipped one. 7 comma 4. We're up here. So you can see that we do get a nice graph that's going to be symmetrical to the line y equals x. I'm going to go ahead and try my best to sketch this without being one smooth curve here. Can we do it? There we go. That's pretty good. Now the line y equals x is this line right here, roughly. And so you can see that, yeah, these are symmetrical about that line. Now, here's the thing. You look at this green graph. This is obviously not a function. It fails the vertical line test, but that just means that the inverse isn't a function. Now, it does have an inverse. It's just not a function. How do we come up with a formula for the inverse? Well, since the inverse won't be a function, we can't use function notation here. So if this is the original function, right, here's the original. This is what we'll call the OG function for the original function. Okay, so the OG function, or maybe I'll just call it f of x. Probably a little bit more appropriate. So the inverse of f of x, one way to think about it is we're just going to swap the x and y. Okay, we're going to take this original equation and just swap x with y. And just know that you're not going to be able to isolate y in a way to where you have a single function. What ends up happening is this is actually the positive and negative versions of a square root function, where the top half is the positive square root function, the bottom half is the negative square root function. So I'm not going to bother trying to solve this one. Just know that the inverse in this case is not a function. And where it says down here, explain why the inverse is not a function, well, it's very simple. It just doesn't meet the characteristics of a function. A function is defined as a relationship where each input only has a single output. There's exactly one output. But as we see in this table and on the graph, we have many, in fact, we have infinitely many points where the x value is associated with two separate y values. It's failing this vertical line test. So that's the basic explanation here. Let's see. So I'll say there are many inputs that have multiple outputs. In a function, you can only have one output for each input. Okay, so let's wrap this discussion up and kind of see where this is going. It says the exponential function f of x equals 2x is graphed below. It kind of looks kind of similar to this exponential function we had up here in number 7. It says first find f of 0, f of 1, f of 2, f of 3. These are just going to be the points that we see on the curve, where f of 0 is going to be the y value when x is 0. If I look at the graph, I see I have a point at 0, 1, so f of 0 is 1. F of 1, look at the graph again and see that when x is 1, y is 2. If I plug in 2, f of 2 is 4. And f of 3, 2 to the third power, be 8. Okay. So now for the inverses, basically what we're going to do here is we are just going to flip the inputs and the outputs. So for each one of these, you're going to just reverse. Oops, what am I looking at here? For each one of these, we are going to reverse the input and the output. I think I already said that, actually. So like for this one, instead of since f of 0 equals 1, we can say the inverse of f of 1 is 0. And just do that for all of these. So this will be that the input's 2, the output's 1. Input's 4, the output is 2. If the input is 8, the output would be 3. Okay, so let's plot these points out. 1, 0 be here. 2, 1 right here. 4, 2. Oh, messed up the last one. 2, 1 is actually right here. 4, 2 and 8, 3. Okay, so we got this nice inverse function here, inverse to an exponential function. Looks basically like that. And yeah, let's close this out. So this particular inverse function, I had kind of pointed it out earlier, and I want to point it out here again. When we have the inverse of an exponential function, we see this one right here. Notice how with the exponential function, we have a horizontal asymptote. With this inverse, we've got a vertical asymptote. This particular function, which is the inverse of an exponential function, actually has a name, and it is called a logarithmic function. Okay, the inverse of an exponential function is called a logarithmic function. Okay, so a logarithm is just an inverse of an exponential. So we're going to get in a lot more detail. This whole unit is going to be about these kind of functions, these logarithmic functions. We're going to go into how they work, how do you graph them, how do they work algebraically, how do you solve equations using logarithms, and so on and so forth, the properties of logarithms, all that good stuff. We'll get into all that in this unit, but today I just wanted to give you a little intro as far as explaining what a logarithm is. And here we go. Our conclusion right here is that a logarithmic function is just the inverse of an exponential function. So that's about it for today. Thanks for watching, and y'all have a good day.